Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. So, you hear the term artificial intelligence, and maybe you picture some sort of inexplicable magic happening inside a computer, right? Well, you are in exactly the right place. Today, we're going to totally demystify how AI systematically searches, reasons, and solves complex problems. As you'll see, it is not magic at all. It's actually just brilliant, structured mechanics. We're going to watch our AI agent go from zero to hero and learn exactly how it navigates massive puzzles to find that perfect answer. Let's dive in.
Here's a really quick roadmap of our journey through this explainer. We'll define AI, look at how computers frame problems, explore blind brute force searching, upgrade to smart heuristics, and then finish up with constraint satisfaction.
All right, let's just jump right into Section 1, Defining Artificial Intelligence. At its core, the literal meaning of artificial intelligence is just a man-made thinking power. But, the working definition from textbook authors Rich and Knight is absolutely fascinating. They define it as the study of how to make computers do things at which, at the moment, people are better. What I love about this is how it perfectly captures the AI effect. It's a completely moving target. I mean, think about how we treat your phone's facial recognition or autocorrect today. Once a machine masters something incredibly complex, we literally stop calling it intelligence. We just call it computation. But AI is fundamentally about making machines systematically replicate the searching and judging that our human brains do every single day.
Just to see how far we've actually come, let's trace a few monumental milestones. This really kicks off back in 1950 when Alan Turing proposed the Turing test, which was a brilliant way to measure if a machine could pass as human in conversation. Just 6 years later, in 1956, the actual term artificial intelligence was born. It was coined by John McCarthy at the famous Dartmouth Conference. Then fast forward to 1997, and we hit a massive cultural milestone. IBM's Deep Blue program defeated the world chess champion Garry Kasparov. That was a real game changer because it proved definitively that machines can indeed outsmart human champions in highly complex strategic environments.
Moving right along to Section 2, Framing the Problem.
Now, how does a computer actually perceive a puzzle? This brilliantly illustrates the concept of a state space using the classic water jug problem. Okay, imagine you have a 4-gallon jug and a 3-gallon jug. Absolutely no measuring markers and a water pump. Your goal is to get exactly 2 gallons into the 4-gallon jug. And AI doesn't just guess here, it literally maps out the problem as a giant graph. That very top node 00 is our start state where both jugs are empty. And the green node at the bottom right, that's our goal state, where the 4-gallon jug has exactly 2 gallons. Every single circle you see is a possible state, and the lines connecting them are the actions we can take.
To actually navigate that state space, the AI systematically applies a set of strict rules. It can only do 3 basic things: fill a jug all the way to the top, empty a jug completely onto the ground, or pour water from one jug into the other until one is full or the other is empty. By methodically applying these simple rules over and over, the AI generates a crystal clear path through the state space to reach that goal of exactly 2 gallons. It basically turns a logical brain teaser into a simple connect-the-dots graph traversal.
Okay, Section 3, Uninformed Blind Search.
So, what happens when an AI doesn't know where the goal is? It has to use uninformed or blind search. We generally compare 2 classic brute force strategies here, and there's a great little memory trick for them. First up is breadth first search, or BFS. Think of BFS as a broad queue. It explores every possible move step by step. It guarantees you are going to find the absolute shortest path, but man, it eats up massive amounts of memory because it has to remember every single state on a given level. On the flip side, depth first search, or DFS, is a deep stack. It dives all the way down one single path as far as it can possibly go. It uses very little memory, which is great, but it's risky. It might water down an infinite path and get stuck forever, completely missing a much easier solution right next to it.
Watching this play out visually is super fascinating. Notice how breadth first search ripples out level by level. First A, then B and C, then D, E, F, G. It's methodical, it's broad. But by contrast, depth first search shoots straight down a single path, A to B to D. Only when it hits a literal dead end does it back up and try E. It's branch by branch. This visual just completely captures the difference in how these 2 fundamental AI strategies operate.
But here's the catch. The crucial point is that while blind search is great for small puzzles, it completely fails on larger problems. Take the traveling salesman problem, where you just want to find the shortest route to visit a set of cities. If you only have 20 cities, the number of possible paths explodes to roughly 16 quadrillion. That's a 6 with 16 zeros. We call this combinatorial explosion. Absolutely no computer on Earth has the time or the memory to blindly search level by level through 60 quadrillion paths. This immense roadblock naturally leads us to ask a huge question. How in the world do we solve these massive real-world problems? How do we give our AI a secret weapon to cut through all this noise and find a solution before the end of the universe?
That brings us right into Section 4, Smart Heuristic Searching.
Enter heuristics. A heuristic is essentially a really smart rule of thumb. It trades the absolute guarantee of finding the perfect answer for finding an excellent answer in a reasonable amount of time. One simple heuristic approach is called hill climbing. Imagine you are trapped in thick fog, and you just keep stepping in whichever direction goes up. But beware, there are three major traps on this landscape, the LPR traps. You might hit a local maximum, where you're at the top of a small hill, but the true goal is on a higher mountain far away. You might hit a flat plateau, where every step looks exactly the same, or you might hit a ridge, where a single step in any direction takes you down, and you actually need to combine moves to make any progress.
So to elegantly fix the problem of wandering blindly or getting stuck on those fake local hills, AI researchers developed the A-star algorithm. This is a best first search that uses a beautifully simple formula. F of x equals g of x plus h of x. An incredibly easy way to remember this is F equals gone plus hope. The g represents the actual cost we have already spent to get to our current spot. That's the gone. The h is our heuristic estimate of the remaining distance to the goal. That's our hope. By combining the two, A-star makes incredibly smart decisions about which path it should explore next.
Tracing this optimal path, we can actually see A-star in action. We start at S. To go to A, it costs 1, that's our gone, and the estimated hope to the goal is 3. 1 plus 3 is 4. Simple, right? Now, if we look at the other route through B, the total estimated cost is 6. Because 4 is less than 6, the algorithm smartly chooses to expand node A. It evaluates the actual cost and the heuristic hope at every single step, which allows it to march straight along the optimal path, S to A to C to the goal G, with a perfect total cost of 6.
Finally, let's look at Section 5, Constraint Satisfaction.
In many AI scenarios, the goal isn't actually finding a path through a map. It's discovering a state that obeys very strict rules. Think of the famous math puzzle send plus more equals money, where every letter is a distinct digit from 0 to 9. We solve this using constraint satisfaction. First, we propagate constraints. Look at the thousands column. Adding two single digits, S and M, can only ever generate a carry of 1. Therefore, M instantly must be 1. Once we know M is 1, S must be 9 to generate a carry, which means O has to equal 0. The AI ripples these known constraints through the puzzle, drastically shrinking the possibilities, and then makes guided guesses for the remaining letters until the whole shebang clicks perfectly into place.
And that brings us to the end of our journey today. We've seen that the magic of AI isn't magic at all, is it? It's brilliantly structured logic. From mapping a state space, to calculating the gone plus hope of A-star, to propagating constraints, AI is just a massive triumph of methodical problem solving. So I'll leave you with this final thought to chew on. If these basic rules and heuristics can conquer puzzles this complex in literal milliseconds, what massive, real-world mysteries will artificial reasoning unlock for us next? Thank you so much for exploring this with me today, and I really encourage you to dive even deeper into this fascinating field. Keep exploring.